All right, let's get started. So as I have announced in the previous lecture that your exam number 2 will be next week, next Wednesday, actually. So 1 week from now, on October 25th, in the class, just like you had your exam number 1. So it will be the same format, 100-mark exam, and it will be during the class times. And of course, everything will be very similar to your exam number 1. I'll post a few sample questions from previous year's exams, but keep in mind that there could be some questions regarding BJTs, which were part of exam number 2 during the previous years. Please disregard them at this point because we haven't gone through BJTs in the class. So even though they would have been the part of, let's say, exam number 2 in previous years, they will not be part of exam number 2 this year, right? Because we haven't covered them in class. So if you see any BJT related question or a bipolar junction transistor related question in the sample exam papers, please disregard them. Okay. Any questions? Okay. A few other announcements that your homework 5 has been posted. It will be due on October 27th. So that will be next week on Friday. And we'll discuss that what is there in homework number 5 and how to solve those as well. Along with that, your lab 5 notes are also uploaded. Again, you'll have 2 weeks to complete these labs. I'll leave it up to you and your UPIs to manage when you want to finish the lab within these next 2 weeks. But this is a very fun lab. So it's a tone control lab where you'll have you'll use an example music file. So I posted 2 examples of the music files that you can use in this lab, but you can use any other music file of your own. So what you'll do is that using an op-amp, you'll control the tone of that music file. And you'll see that it will be a very fun lab to work with, and please work with your TAs or your EPIs to complete this lab within the next 2 weeks, specifically by November 2. Okay. And all the details are posted in this particular PDF document. All right. Now, coming back to what we had been discussing in the previous few lectures, how to solve transistor-based amplifiers. So first of all, you have to find the operating point, the DC operating point of your operation of the MOSFET. And to find the DC operating point, what we have done in our homework number 4 and also on the examples that I have shown in class is that you assume an active region and you use the formula of ID equal to half of K times VGS minus VD whole squared, which means that your V overdrive will be equal to square root of twice ID over K. And K is equal to your mu times UX times W over L, which is also equal to K dash or K prime times W over L. And if it is not mentioned in the question, then just assume 1 plus lambda VDS is almost equal to 1, which means that the effect of channel length modulation is minimal. Lambda is your channel length modulation parameter as we have discussed in the past. And what this will do is that it will add one additional term. One additional term will be multiplied with this ID equation. So ID will be K over 2 times VGS minus VD whole squared multiplied by this 1 plus lambda VDS term that is mentioned over here. But this is only when you have to consider the channel length modulation. If in the question it is mentioned that do not consider channel length modulation, you do not have to consider this 1 plus lambda VDS term, and this can be considered as equal to 1 because as you again know that lambda is very small. So lambda times VDS is very small. 1 plus lambda VDS will be almost equal to 1. All right. So using these equations, you will eventually estimate what is your ID and what is your VOV. And the way you can verify whether you are still in the active region is that, of course, your VGS needs to be more than VT. Your gate to source voltage has to be more than the threshold voltage. And VDS, which is the drain to source voltage, that has to be more than VGS minus VT. So drain to source voltage has to be more than your overdrive voltage, and VGS has to be more than your threshold voltage. So that's the way you can verify whether you are actually in the active region or not. Another way to understand VDS to be greater than VGS minus VT, or another way to represent the same equation, is that your VGD has to be less than VT. And we proved this in the previous class, that why VGD needs to be less than VT for VDS to be greater than VGS minus VT. So you can use either of those two equations to verify whether you are in the active region or not. Okay, you can calculate your small signal parameters. So you already have your equation of ID as this when you are considering this 1 plus lambda VDS term, this additional channel length modulation parameter term. If you don't consider it, then you can just have that additional term to be almost equal to 1 to make this expression much more simpler. Your GM is basically a derivative of your ID equation with respect to VGS. So if you take a derivative of your ID equation with respect to VGS, you'll get your GM or transconductance. Remember, this is transconductance, which means that one quantity will be at the input, the other quantity will be at the output. That's why we are calling about trans. That means it is transferring one quantity at the input to another quantity at the output. Now, why is it transconductance? That is because your input quantity is voltage, your output quantity is a current. And output over input, that's your transfer function. That's basically a conductance. Current over voltage is a conductance. That is equal to 1 upon resistance from Ohm's law. Okay, so that's your transconductance formula. So your ID is the output current. VGS was the input voltage. So if you take the derivative of ID with respect to VGS, you'll come up with these equations that GM could be twice ID over V of V. We prove these equations over and over again in the class, which will be equal to K times V over drive, which will also be equal to square root of 2 times K times ID. Okay, so that's your GM or transconductance. The output conductance or GO, so that's the conductance at the output. That is again your del ID over del VDS, or the derivative of your ID equation with respect to VDS. Remember, in this case, you are talking about the output conductance. And in this case, you're talking about the transfer conductance or the transconductance. Okay. So output conductance is output current change in delta change in output current divided by delta change in output voltage. So it's just again a current over voltage term, but both the current and the voltage is at the output. That's why it's called the output conductance. The previous one was transconductance because you had a delta change of output current divided by delta change in input voltage. Okay, input and output are separate quantities. So input voltage is your VGS, output voltage is VDS, and output current is ID. So you again already you have proved this that your GO or the output conductance is equal to lambda times ID, which means RO, which is the output resistance, is 1 upon GO, which is equal to 1 upon lambda ID. Again, something that we proved, I think 2 or 3 lectures earlier. Okay, so at this point, you have a very good idea about where your transistor is biased, what is your VGS, what is your VDS, what is your V overdrive, what is the current flowing through the device, what is the transconductance of the device, and what is the output conductance or the output resistance of the device. So you have all the different properties that are needed to analyze any kind of transistor-based circuit. So these are the properties or these are the equations that we'll be using to analyze any kind of transistor-based circuit. Now, to find out the small signal gain, which we'll be discussing today, for that, we'll be analyzing the small signal equivalent circuit or the linear equivalent circuit that you have learned during your op-amp, when you discussed your op-amps. And we have also looked into what is the linear equivalent circuit or what is the small signal equivalent circuit for the MOSFET as well, which was this one. That in the simplest form, it's a VGS that you apply at the input side. And because of application of that VGS, you have a GM times VGS current at the output side. Remember, again, these are AC quantities. So VGS is an AC quantity. GM times VGS, that's an AC current. So you apply an AC voltage, you get an AC current at the output. And it's called a small signal AC equivalent circuit model or the small signal or the linear equivalent circuit model because we are only considering the AC voltages and currents at this point. And why is that again? Because with this model, we'll be trying to figure out what is the gain of your MOSFET-based circuit. And by gain, we always mean AC gain. You have a sine wave at your input. What is the amplified version of the sine wave you'll have your output? That's what you're interested in finding out. Okay. Now, you can introduce a little bit of non-linearity here. If it is mentioned in the question that you can consider RO then you do consider RO, which will be in parallel to this dependent current source, because again, you know that the non-ideality in any current source is a parallel resistance. The non-ideality in any voltage source is a series resistance. So as you place this RO resistance in parallel to this dependent current source, you'll get your non-ideal representation of the small signal AC equivalent circuit. Of course, there could be many other non-idealities that people can introduce. We'll look into those a little bit in our later lectures. But at this point, this is all the non-ideality that we'll be working with, that this current source is non-ideal. It has a parallel resistance along with it. Okay. There could be other non-idealities like capacitances at every node, which we'll not discuss right now. We'll discuss that a little bit in our later lectures, but they'll be more important when you go for graduate studies or when you are actually doing a research project and your capacitances become important, specifically at high frequencies. At low frequencies, capacitances are open because the impedance of a capacitance is 1 upon j omega c, which means when omega is equal to 0. So your impedance of any capacitance is 1 upon j omega c. So if your omega is 0, which means you are at DC or 0 frequency or very low frequency, your impedance of the capacitance will be very, very high. Ideally, at 0 frequency, the impedance of a capacitance will be infinite. And which means that the capacitance is basically an open at 0 frequencies. However, at infinitely large frequencies, all capacitances work as shorts because omega is infinite. So 1 upon j omega c is equal to 0, which means that the impedance or the resistance of a capacitance at very high frequency is equal to 0, which means it becomes a short. So capacitance is an open at 0 frequency, capacitance is a short at very high frequency. So if you are designing circuits for very high frequencies, you cannot ignore the capacitances that are present at every node, and those will add more and more non-idealities. We'll not discuss those non-idealities right now, but it's good to keep in mind that there are more non-idealities than what we are showing right now. Right now, we are only showing that you have this RO as your non-ideality. Okay, so that's your small signal equivalent circuit, and you can estimate any kind of cutoff frequencies based on if you see any kind of filtering effect happening at the input side or output side. So we'll look into that. We'll also learn how to do this using the open circuit time constant based method, which we have already looked into a little bit during your homework number 3, I believe. Okay, so a few other things that we want to discuss first, that the biasing for MOS amplifiers, how do you actually do a biasing of a MOS amplifier? There are two general approaches. One is called AC coupling, that will couple the AC signal separately than the DC signal. Again, a few examples we have looked into when we are solving your homework number 3. And there is another approach called DC coupling. What is AC coupling is, I think you'll understand it better when you show a picture. So for example, if you look into this particular diagram over here, and as you see that this is very similar to what you had seen in your homework number 3. Only difference is in your homework number 3, you had an op-amp. Now here in this circuit, instead of an op-amp, we just have a MOS transistor. And of course, this RD resistance. So this part was replaced by a op-amp in your homework number 3. But everything else was very similar. That you had a VDD over here, you had RB1 and RB2 connecting the VDD to ground, which means that you'll have a division of voltages from VDD to ground. And at the middle point, you'll have a voltage which will be equal to, let's call this Vx. And you already know that Vx is equal to RB2 divided by RB1 plus RB2 times your VDD. So that is again something very similar to your homework number 3 problem, one of your homework number 3 problems, that you found out what is the voltage, what will be the DC voltage at this point. And even though there are other components connected at this point, why are you saying that the voltage is just a division between the RB1 and RB2 resistances? That's because looking into this side, what you see a capacitance. In terms of DC, we already discussed that what is the impedance of a capacitance at DC? It's infinitely high, right? 1 upon j omega c. At DC, omega is equal to 0. 1 upon j omega c is equal to infinite. So looking into this left direction, left side, you'll see infinite impedance of the capacitance, which means that there will be no DC current flow on the left side. This is another way of saying any capacitor blocks DC. So you may have heard about this sentence that any capacitance will block your DC currents. And that's the reason that capacitance has an impedance of 1 upon j omega c, which is an infinite impedance at DC or zero frequencies. And that's why you do not see any DC current through a capacitance. If you have infinite resistance, can you have a current? No. How much ever voltage you apply across that infinite resistance, you'll not see any current at all. Because a finite value divided by an infinite value is equal to 0. So your current will always be 0. The DC current will always be 0 through this capacitance. Again, on the right-hand side, you see the gate of this transistor. We already discussed that for a MOSFET, it's a metal oxide semiconductor structure, right? So you have a metal gate, you have some kind of an oxide in between the metal and the semiconductor. So this oxide layer stops any kind of current to flow through. So there cannot be any current flowing into the gate because of the presence of the oxide layer. And that means you have an infinite input impedance at the gate. This is very similar to what we discussed with op-amps, that for op-amps, there is an infinite input impedance, there cannot be any current flowing into the gate. Now you sort of can guess why. That if you create an op-amp for which the input stages go to the gate of a MOSFET, there cannot be any current flow into that gate of the MOSFET. Because at the gate of the MOSFET, you have silicon dioxide, which is an insulator. There cannot be any current flow through an insulator. There could be some amount of leakage, very small amount of leakage, but let's ignore leakage at that point, at this point. So there cannot be any current flow on the right-hand side as well, which means all the current flows from VDD to ground through these two resistances. And that's why the voltage developed at point X will be this much, will just be a function of the RB1 and RB2 resistances. There will be no effect of this capacitance on the left-hand side. There will be no effect of the gate on the right-hand side because the DC current flowing into left or right, both are equal to 0. All right. So again, something that we have seen earlier, nothing new. So what we are doing in this case is actually you're biasing the gate of the MOSFET, you're biasing the gate of the transistor at this voltage Vx. So if your RB1 and RB2 are equal, then you're biasing the gate of the MOSFET at VDD over 2. That's just a DC point. Remember that from VTC, from the voltage transfer characteristic, you know that you can expect gain only in the middle region of the VTC, which means that you have to bias the transistor or you have to eventually bias the op-amp when you create an op-amp with your transistors near to the middle of your VTC range. So if your RB1 and RB2 are similar, your Vx will be VDD over 2, and that's the point where you will bias your transistor. And then if you apply an AC signal, this Vs is an AC signal. Only then, if you apply an AC, you'll expect an AC gain at the output. You'll see an amplified version of the input AC signal at the output. If you don't bias it in the correct region, you'll not see any kind of gain. If this voltage is 0, if this DC voltage is 0, or if this DC voltage is equal to VDD, then you'll either be at this point, which is a very small DC voltage, or you'll be at this point, which is again a very large DC voltage. So this is the V input, and this is the V output in your VTC, right? So if your input voltage is very small, the slope of this curve is 0. So you don't get any gain. If the input voltage is very large, again the slope of this curve is 0. So you don't get any gain. Only if your input voltage is in the middle of your range of operations, only then you expect a finite amount of gain because your slope is not 0 and hopefully it is much more than 1. If it is more than 1, you get a gain which is more than 1. All right. So at this point, you want to apply an AC signal now. How are you applying the AC signal? You are applying the AC signal through this capacitance again. So for example, this is the AC voltage source, and this RS is the non-ideality of the AC voltage source. Because it is a voltage source, the non-ideality is a series resistance. That AC voltage is getting coupled to the input of your MOSFET, to the gate terminal of your MOSFET using this capacitor. And again, as you have learned that for very high frequencies, capacitance is a short. So for AC frequencies, assuming that this capacitance allows that AC signal to pass, you will see that the AC signal will be available at the input of the MOSFET. But the DC signal will not be available on the left-hand side. So in terms of DC, this point and this point, the left and right-hand side of the capacitance will be decoupled. But in terms of AC, they will be coupled, which means that the AC signal seen at the left and right-hand side will be same for the capacitance, but the DC signal can be very different, and that's okay because you want to have a DC bias point for the MOSFET in the region where your slope of the VTC can be maximized, and at that point you want to apply an AC signal. So that's why you are coupling it with a capacitance. A capacitance lets the AC signal flow, but it will block the DC. But then again, remember that because you have a capacitance over here, and on the right-hand side you have a resistance to ground, you have another resistance which goes to VDD, which is an AC ground. Remember that VDD is an AC ground because there is no AC fluctuation in the supply. So in terms of AC, on the right-hand side of the capacitance, what you have connected is RB1 connected to ground in parallel to RB2, which is also connected to ground. So RB1 is connected to AC ground. RB2 is also connected to AC ground. So in terms of AC, what you have is, looking from the left side, you have this capacitance C1, and then you have a resistance to ground, which is basically your RB1 parallel to RB2. So that's what you see looking from the left-hand side, that there is a capacitance and then there is a resistance to ground. What is this network? That when you have a series capacitance and then a parallel resistance to ground, what is this network? Is this a low-pass filter or a high-pass filter? Again, something that we have already learned. It's a high-pass filter, exactly. So a capacitance, a series capacitance followed by a resistance to ground, it's a high-pass filter. You can readily prove this because, and again, I'll just show how to prove this. I'm assuming that most of you already know how to do this calculation. So if this is a capacitance, the impedance of the capacitance is 1 upon j omega c. In Laplace domain, you can write it as 1 upon SC because S is equal to j omega in Laplace domain. So the impedance of the capacitance is 1 upon SC. The impedance of the resistance is R. The voltage that you develop, so if this is your V in, the voltage that you develop at the output, let's call it V out, that would be equal to R divided by 1 over SC plus R, correct? Which you can write as SCR divided by 1 plus SCR. Okay, so now what is happening at zero frequencies? To understand whether a circuit works as a low pass or high pass, you can consider two frequencies. One is zero frequency, one is infinite frequency. What is happening at zero frequency? At zero frequency, the numerator is becoming zero. So this is becoming zero. S is equal to j omega, omega is equal to 0, your numerator becomes 0. So the output voltage that you get at zero frequency is equal to 0. The output voltage that you get at infinite frequency, omega is equal to infinite. So S equal to j omega equal to infinite. So 1 upon SC becomes 0. So this term becomes 0 at infinite frequency. So at infinite frequency, your output is R divided by R, which is equal to 1. So your transfer function, so if you are plotting your V output with respect to frequency, at zero frequency, your output is 0 because your numerator had become 0. At infinite, so that's your point. At infinite frequency, your output is R divided by R, which is equal to 1. So you get basically that's the transfer function. So that multiplied with V in will be giving you the voltage. So at infinite frequency, you have the full V in voltage. And somewhere in between the zero frequency and infinite frequency, you'll have the cutoff frequency. And that cutoff frequency will be how much? That cutoff frequency will be 1 upon RC. Right? Because remember again, from this particular formula that you have, if your omega is equal to 1 upon RC, your numerator will become 1 because S equal to j omega. If you are taking just the magnitude of it, replace S with 1 upon RC, So 1 upon RC will cancel out with this RC that you have in the numerator. So let me write it down again in a phrase way that you have SCR divided by 1 plus SCR. So the magnitude of this at the frequency when you have 1 upon RC, omega is equal to 1 upon RC, your numerator will become 1 and your denominator, the magnitude of that will become square root of 2 because this is 1 and this is S times CR, S is equal to J omega, omega is equal to 1 upon RC. So that RC and the 1 upon RC will cancel. So you'll have square root of 2 because you're taking the magnitude of a complex quantity. Right? So this becomes 1 upon square root of 2. That's the voltage. In terms of power, you'll have the square of that. So your power will be half power point. So that's your bandwidth. Your bandwidth is your half power point or your minus 3 dB bandwidth point, right? So your bandwidth will be 1 upon RC, and this will work as a high pass filter. Again, similarly, you can prove that if you have a resistance in the series path and a capacitance in the path to ground, it becomes a low pass filter. It's just a dual of this circuit. If you just replace the resistance and the capacitance, it will become a low pass filter. All right. So why we are discussing all of that is just because if your frequency is beyond this cutoff frequency of the high pass filter, if the frequency at which you are operating, so let's say this is the frequency at which you are operating, the output of your high pass filter will be equal to the input of your high pass filter, because as you just saw that the output will be equal to input, or the transfer function will be equal to 1 at high frequency, that very high frequency. So as long as your frequency is higher than your pole frequency, as long as your frequency is higher than this cutoff frequency, your output of the high pass filter, that is this point, will be equal to the input of the high pass filter, which is at this point. So the AC voltage that you apply at the left side of the capacitance will be same as the AC voltage that you apply at the that you have at the right hand side of the capacitance. So this is called AC coupling, that you are coupling the AC with respect to this capacitance or using this capacitance, and you're applying the DC voltage by having this voltage division. That is just one example of how we can apply a DC voltage at the gate of the MOSFET. So you're applying a DC, also you're applying a AC. So you're adding the AC and DC together with help of this circuit. So that's one way to do it. Okay. So that's called AC coupling. What is DC coupling? DC coupling is that you do not have this capacitance at all. Let's just assume that you do not have this capacitance. So in that case, you have to ensure that, okay, you have an AC coming in from the left-hand side. But let's say because you do not have this capacitance anymore, there's no point trying to bias this DC of the gate of the MOSFET using these resistances, because this network will not work. Because at this point, if you're trying to now find out the effect of the voltage value of Vx, it will not be a voltage division between RB1 and RB2, because on the left side, if you do not see this capacitance, you'll see this RS resistance, and then there will be some amount of current flowing to the left-hand side as well. And the voltage at this point will not be this simple division of voltages between RB1 and RB2. So there's no point having RB1 and RB2 anymore. What you need to do is that you need to ensure that the voltage source has a DC point which is close to the most optimum VTC point for this particular transistor. So that's called DC coupling, that you will not do any kind of biasing, or you will not do any kind of coupling of AC signal at the transistor. You'll just assume that this voltage source is good enough that it can provide the correct AC as well as the correct DC. So for example, let's say you needed a 5-volt DC here, but the DC of this voltage source was 0 volt, it had a 10 millivolt AC swing. So DC was 0 volt, but you had a 10 millivolt AC swing. If you need a 5-volt voltage, DC voltage at this point, you have to create this DC biasing network, and you have to couple the AC signal using the capacitor. But imagine that this DC voltage source itself had a 5-volt DC and a 10 millivolt AC signal. So you're meeting your requirement that you needed a 5-volt at the input of the gate in terms of DC, but your voltage source already gives you a 5-volt DC. Then you can directly couple or DC couple the source with your input transistor. Okay, so that is actually called DC coupling. And when AC coupling and DC coupling will be useful, so that's written over here. So for example, you can put coupling capacitor for any kind of time varying input signals such as audio or video. You can put those capacitances in series at the output or input or output branches. So for example, here at the output side, you're also coupling the output of the MOSFET or the output of the amplifier to this point, to your VO. So whatever DC your amplifier had, so whatever DC point, let's say this DC point is also, for example, 6 volt, right? So the left-hand side of the capacitor can have a DC voltage of 6 volt, but right-hand side of the capacitor can have a different DC voltage. Right? So you can couple it to the next stage. So in this way, for example, let's say you have a 2-stage amplifier, that this is your first stage, and again you are connecting the same stage again at the output of the first stage. So you can just have 2 stages of amplifiers. You have also learned this in the beginning of our course, right? That if you have 2 amplifiers back to back, and the first amplifier has a gain of 10, the second amplifier also has a gain of 10, the total gain you can expect is 100, 10 multiplied with 10. So you can just connect like one amplifier after another, and in that case, this AC coupling really helps you a lot, because then your DC points are decoupled with each other. So remember that at your, let me clear some of these things up. So remember that you want 5 volt at this point at the input of the transistor, but let's say at the output of the transistor you have 6 volt DC. So you cannot connect the 6 volt DC directly to the next stage, which will be, let's say, another MOSFET. So if you do that, then the gate of the MOSFET will get 6 volt, and it may not work properly according to the VTC. Okay. Or let's just say it is 8 volt instead of 6 volt, then it will probably definitely not work properly according to the VTC. So what you can do is that, because you have this coupling capacitance, you can again create a biasing network at the input of the second MOSFET using the same kind of RB1 and RB2. So you have this VDD, you can connect another RB1 and RB2 over here. Let's say we do not have this RL. So in that way, you can create a DC point here, which will again be 5 volt, instead of this being 6 volts or 8 volts, which if you directly provide it to the gate of the next MOSFET, it will not work. But by creating this AC coupling, you can make sure that each stage of the amplifier is, as you're designing each stage of the amplifier, they work well in a standalone fashion. Also, when you put them together, they work in a good manner, right? So you get the gain of 10 and 10 in both cases. If you just DC coupled them, if you just directly connected them one after another, even though standalone, or if you do a standalone testing, they can give a gain of 10 and 10, but when you connect them together, because of the mismatch at the DC points, they will not give you a gain of 10 and 10. They will probably give you something else. And in worst case, one of the amplifiers may not give you any gain at all. Right? So that's why using AC coupling, you can always make sure that each of the amplifiers are working well in a standalone fashion. Also, they are working well when you put them together. Okay. So this is one strategy. So there are some common biasing strategies. So this is called a fixed VGS biasing, that you have a fixed gate to source voltage for this MOSFET. What is that gate to source voltage? That is equal to RB2 divided by RB1 plus RB2 times VDD. That's your gate to source voltage for this MOSFET, right? So it's called a fixed VGS biasing. You're fixing VG to be more than VGS to be more than VT. You're connecting VS to ground. And this is the Thevenin equivalent circuit for your AC network. That for your AC network, you have your RB1 in parallel with your RB2, and that's how you should analyze this circuit when you are trying to find out what is the AC voltage at this point, and eventually how much would be the AC voltage at this point. So we look into those scenarios in today's lecture. Okay. So that is your biasing by fixing your VGS. You can also bias the transistor using by fixing the VG and then connecting a resistance at the source. So this is called degenerating the source of the transistor. Why is it called degenerating? We'll see later that as you apply a degeneration resistance, the gain of the transistor or the gain of the system will reduce. When you apply this degeneration resistance, eventually we'll see the gain will reduce, and that's why it's called a degeneration resistance. It degenerates the gain. We'll see that later. But now we are going to see how that helps in your biasing. So if you have a degeneration resistance, what you will see is that you can apply a fixed VG, you can apply a fixed gate voltage at the gate of the transistor, and you can fix a particular amount of current. You can actually, let's say, put a current source on top of the transistor. What that will do is that it will fix the current flowing through this transistor. And depending on how much current you're putting over here, there will be a particular amount of voltage drop across this resistance. You have also solved some of this type of biasing questions in your homework number 4, right? That you have a fixed amount of current, let's say 2 milliampere. You wanted to find out what would be the value of this resistance so that your transistor is still in the active region, right? So somewhat of that sort you have already solved in your homework number 4. Now, as you're applying this some amount of current at your drain terminal, the same current will flow through the source terminal as well and will flow through the resistance. So there will be a particular amount of drop across this resistance. If you have this particular amount of drop across this resistance, your VGS will become a function of how much current you are putting through the device. As you increase the amount of current, the amount of voltage drop across this resistance will increase. That means the source voltage will increase. So the gate to source voltage will start reducing. So at some point, you'll see your gate to source voltage will become less than your threshold voltage, and at that point the transistor may stop operating well, right? It will go into subthreshold region or cutoff region. But by using this kind of resistance at the source, what we'll see later that the gain reduces, the gain degenerates, but also the gain becomes much more stable. So we'll look into that, and that is the main advantage of using this degeneration resistance at the source side. But something that you need to keep in mind that as you are applying this degeneration resistance, your VGS, let's say for example, as you increase this degeneration resistance, your VGS keeps on dropping. So at some point, there is a risk that your transistor will go into cutoff region. All right. So this is what we are mentioning here, but we'll prove this in the next lecture. That will be in Friday's lecture. But adding a degeneration resistance, this RS1, will reduce the circuit's voltage gain. We'll eventually see that earlier in the past, like in the previous lecture, we have already proved this, that if you have a resistance connected at the drain, and if this is your circuit that you're applying your input voltage over here, let's say that's your AC input. I'm not drawing the coupling rate, capacitances or any kind of DC biasing resistances here, but let's just assume they are all there. We just want to know what is the AC input and what is the AC output. So if that V in is your AC input and V out is your AC output, if this is equal to RD, we already have seen in the previous lecture that V out will be equal to GM times RD times V in. Okay, which means that your gain is GM times RD, or in this case, it is actually minus, and we'll also prove that, we proved that in the previous lecture that why it will be minus, because the current source that you have in this case, that current flows from drain to source. So if you want to, so the current flows in this direction. If you want to find out what is the voltage developed across this RD resistance, the current is flowing into this direction, but you're trying to find out the voltage in this direction. That's why the gain of the circuit became minus GM times RD. Again, something that we have looked into in the last lecture. So what I'm trying to say here is that your V out will be minus GM times RD, that is the gain of the system, times V in. And you can also write the same equation intuitively, right? Minus GM times V in is the current that is flowing through the device. Minus GM times V in. So transconductance times input voltage. Transconductance times input voltage. That's basically the current that is flowing through the device. Right? That current multiplied with the resistance that you have as a load in terms of the AC, that gives you the output voltage. Current multiplied with resistance gives you voltage, Ohm's law. Right? So if Gm times Vin is your current, then Gm times Vin times RD is your voltage. So that's why at your output, you'll have this, the absolute value of the gain will be Gm times RD, and Gm times RD times Vin will be the absolute value of the voltage at your output side. Okay. So your gain in this case is minus Gm times RD, and the absolute value of the gain is Gm times RD. Usually Gm times RD, for most of our cases, we'll look into a few examples in our next lecture. We'll see Gm times RD will be in the range of maybe 10 or 20 or 30. But in this case, when you have this RS resistance, again, we'll prove this in our next lecture with the AC small signal model, and we'll see the gain of this circuit becomes minus RD over RS. So there is a big difference here, that the gain of this system will be minus RD over RS, whereas the gain of this system was minus Gm times RD. You'll see that for standard values of Gm, RD, and RS for any transistor-based network, Gm times RD will be much more than RD divided by RS. So this could probably be a value of 5 or 10. On the other hand, this could be a value of 30 or 50. So that's possible. Okay. So that's why we are saying that the circuit's voltage gain will be reduced. For now, let's just assume this to be true, that the gain of this system is minus RD over RS. We'll prove this in Friday's lecture. But yeah, what I'm trying to say here is that adding this degeneration resistance will reduce the voltage gain. So what you can do at high frequencies is that you can include a bypass capacitor C2. You can include a bypass capacitor C2 in parallel to this RS1 resistance. What that will do is that it will short circuit this RS1 at high enough frequencies. Again, remember that capacitance is a short at high enough frequencies. Capacitance is an open at DC. So what this is doing is that at high enough frequencies, this RS will become short through this capacitance, because this capacitance will be shorted to ground at high enough frequencies. And what is meant by high enough? That is higher than the pole frequency that we'll have for this RC network. Okay. So if this capacitance, let's just assume for a moment that this capacitance shorts the source of this transistor to ground, then you effectively have this circuit. There is no source resistance anymore if the capacitance shorts that resistance to ground. Right? Effectively, you have the circuit that I have drawn on the right-hand side, because the source or the source terminal of the MOSFET is directly connected to ground through the capacitance at high enough frequencies. Okay, remember, let's just talk about infinite frequency for now. So at infinite frequency, you see this circuit instead of what is drawn on the left. Right? So at high enough frequencies, the gain of the circuit becomes minus Gm times RD. So that is one way to get the gain back. That is one way to get the gain back at high enough frequencies. So your gain, if we are plotting gain with respect to frequency, and if you have this RS1 and C2 network at low frequencies, or let's say at 0 frequencies, the gain will be, and I'm not considering the minus sign over here. Let's just talk about the absolute value of the gain. So the absolute value of the gain at low frequencies will be RD divided by RS. At high frequencies, it will be Gm times RD. And you'll see a transition in between somewhere, depending on the pole frequency, which will be equal to 1 upon RC given by this RS1 and C2 resistance. So as you see that this also works as a high pass filter, the RS1 and C2 resistance. This also works as a high pass filter. We told that C1 works as a high pass filter. C1 and the combination of this RB1 and RB2, they work as a high pass filter. The C3 in combination with RL, that also works as a high pass filter. And this RS1 and C2 combination, that also works as a high pass filter. Why am I calling it a high pass filter? Because as you see that at low frequencies the gain is small, at high frequencies the gain is larger. That is the definition of a high-pass filter, that you have more gain at higher frequencies, you have less gain at lower frequencies. So the combination of RS and C2 will also work as a high-pass filter, and that will give you back the amount of gain that you lost because of this RS1. So if your operating frequency is here, then your gain is GM times RD. Your gain is not RD over RS when you have this RS and C2 combination. But without the C2, your gain is RD divided by RS. Your gain is much smaller. So what is the advantage? One advantage, we'll talk about it later, that it stabilizes the gain. So this is also called linearization or stabilization of the gain. And we'll talk about that later when we discuss the AC equivalent circuit for it. But the other advantage is something that we are talking here, that, okay, so maybe we'll be talking about it here, that, yeah. So you can find out what would be your VGS, what would be your ID for this particular circuit where you have your degeneration resistance as well as a bypass capacitance connected here. And why is this capacitance called a bypass capacitance? Because it bypasses this resistance at high frequencies. That's the easiest way to understand why it is called a bypass capacitance. Now, of course, let's discuss about the linearization or the stabilization of the gain factor when we actually do the AC small signal model that we'll be doing on Friday. And then it will be easier for you to understand that why sometimes we prefer degeneration of the gain. And it's basically because we have talked about this a little bit when we were discussing op amps as well, that what is the gain when you have the degeneration resistance? It becomes minus RD divided by RS. It becomes a ratio of two resistances. You'll see that if you buy two resistances from the market, if they are of the same batch, even though the resistances will vary a little bit, they'll probably vary in the same direction if they're from the same batch. So if you have RD as 100 kilo ohm, RS as 50 kilo ohms, if because of process variation, RD becomes 101 kilo ohms, RS will probably become 50.5 kilo ohm or very close to 50.5 kilo ohm. So the ratio of RD and RS will be very similar. On the other hand, this GM times RD, this gain can be anywhere. Your GM of one transistor versus the GM of other transistor could be very different. And you probably have seen this in the lab, that maybe the gain of let's say person 1's op amp has a very different gain from person 2's op amp. It is possible, right? The threshold voltage of the MOSFET is very different for each other, right? That's something that you have already seen in the previous lab, that some of you had a threshold voltage of 1.7 volts, some of you had 1.9 volt, some of you had 2 volt, because there is always process variation. And because of those process variations, the threshold voltages will be different, the GMs will be different. So this GM times RD is not something that you can control. On the other hand, RD divided by RS is something that you can always control. So that is the main reason why people use this RD and RS network as a stabilization factor, or a gain that can be made much more stable than your GM times RD gain. So that's the use of this RD over RS. But if you do not want the degeneration, you can always use this bypass capacitance so that you can get back this GM over RD, GM times RD gain. We'll talk about it more in the next lecture where we will be showing the AC equivalent circuits. But I just wanted to give you a flavor of what is coming next in Friday's lecture. Okay. Thanks everyone, and I'll see you on Friday.